The math behind molecular magic, how direct and exchange integrals explain hydrogen bonds, discover the hidden forces that govern the hydrogen bonds with a deep dive into the essential integrals of quantum chemistry. And we see that these pop up in the hydrogen molecule ion, so H2 plus, where we have a proton here, and only one electron. And so, as you might imagine, the proton-proton pairing is going to cause a problem. So let's check out what we're tasked with doing. Thus, in problem 8.8, we're tasked with evaluate the direct integral d and the exchange integral x, so equations 8.46 and 8.47, and check them against the answers for equations 8.48 and 8.49. So not just taking the author at their word, we're actually going to find out where these came from. Why do we care? Well, as we kind of discussed in earlier sections, the electron-electron pairing caused problems and thus approximation methods. The same thing's going to happen with the proton-proton pairing and interaction. So with that, whenever we're looking at an ion like this, it's the same typical three-body problem that we had with the two electrons and one proton. Okay, so that's still the pairing between an interaction between the electron-electron, proton-proton causes a problem. And thus we have the electron-nucleus interactions, which is measured by the direct integral. And then we have the electron exchange and quantum correlation for molecular orbital theory, which is measured with the exchange integral. So it's quite a bit to deal with, and these integrals are not necessarily easy, but once you dig through the algebra, it's not that bad either. It's just a lot of note keeping. But we do have a challenge here. And because these are kind of messy integrals, they don't actually do much to sustain us as we get into more larger body systems. So what is an approximation method that most of you have heard of that are used to help with these integrals? Because there are a few, but there's a very famous one, especially with the new movie that came out. But like I said, because this is pretty mathematically intensive in terms of algebra and note keeping, don't forget to check out the PDF where you have all the little rigors in it. You can access that using the link below. So that will definitely help you, or if you just want it for your collections, feel free to have it. And if you find value in this content, you can make a big difference by liking, subscribing, sharing it with a friend, or donating through Buy Me a Coffee. No account needed. Your support means the world to me and will help keep this journey going. So with that, let's get into our question. Okay, so first, we have to define what these terms are in terms of the expectation and the integrals. So for the direct integral, we have the Bohr radius out front. That was just due to the factor of a over r2. And then we have some wave function, okay? Now, if you remember, this is still in the chapter with the variational method and the variational principle. So we're going to choose a trial function that looks like the solution or the ground state for something like the hydrogen atom. Okay, so keep that in mind. That's going to come in from equation 8.37. But we have a lot of terms here. What is the direct integral, which I have r1 here and r2 here, but that's equivalent to the others where I put r2 and r1. What exactly is r2 and r1, right? That's what we're going to have to use geometry to help us solve for, in particular finding the bounds on our integrals here for the expectation value. So we plug in the psi star psi, again, all of that's in the PDF. We get this normalization factor out front, good. And then we see that we're left with the exponential of r2 and r1. But let's go look at the geometry to help us figure out the limits and r2, r1. So here, what we're doing is we're putting one proton at the origin. Of course, we can define our coordinate system however we want. And we're putting another one up top on the z-axis. And what we're saying is that the distance between proton 1 and proton 2 is capital R. And thus, from the origin to electron, we have lowercase r. So by the law of cosines, since we're not a perfect right triangle, we know that the distance from proton 2 to the electron is r prime. And that's what we're defining this as. Here, lowercase or little r without a prime is r1, and r prime is r2 in the expectation values. And that comes from the, again, the law of cosines. Geometry is never going to leave you in physics, and you have to be conscious and aware that you can manipulate these coordinate systems to make your life easier in finding out these values. So the goal here is just utilize this, and we see that if we want to measure over all space, then the theta here goes from 0 to pi because it's on the z-axis, and that we can go from 0 to 2 pi in the xy plane, and then r, whatever r is, which we're going to end up substituting in for a little r here, that goes from 0 to infinity. So that's what we're going to have to set up and be aware of, but thankfully geometry gets us straight, and we can continue on with this problem. All right, so with that little segue done, we see that our normalization factor being squared yields a pi a cubed, but that cancels with one of the Bohr radius that was in the expectation, so we get a square here. And then as we see for the dv for a spherical element, we have r squared sine theta, dr d theta dv. And like I said, we run dv from 0 to 2 pi, theta from 0 to pi, and r from 0 to infinity. We plug in the value here that came from the law of cosines. And then, of course, the expectation value we're taking is of 1 over r. Okay, so that r cancels with 1 from the Jacobian of the spherical coordinate transform. We're good there. And then we see that the phi integral is trivial, all things considered. That just leaves us with the factor of 2 pi. So our pi and pi cancel. We have one factor of r remaining, which we see here. And thus doing the theta integral first to get rid of this cosine and the sine is going to be the easier step. But clearly, this is not a nice exponential that we've dealt with before. It's not a Gaussian. It's not a straightforward, linear argument in the exponential. So we're going to have to be careful with the substitution. Let's see what we can do for that. So clearly, we could either use the book's intuition or we can make our own. Both will get you there. And what we see here is that getting rid of that square root in the exponential is probably the most important part of it all. So if we let y equal the square root from the law of cosines, then we see that squaring both sides of it gives us a much easier thing to take the derivative of. So then when we do implicit differentiation on y squared, and take d by d theta on both sides, we end up with a 2y dy d theta. And then on this side, clearly little r makes nothing, big R makes nothing, but that cosine goes to a negative sign. So we have a 2 on this side that cancels with the 2 on that side, and both of the negatives cancel. So we get something pretty nice, all things considered. And that gives us a y dy equals little r big R sine theta d theta when we push this d theta term over to the right hand side. And if we solve for d theta, we just divide by our r big R sine theta to that side, and this will simplify quite nice. However, in doing a substitution, it makes no sense to keep the bounds the same at this rate because we don't want to have to back sub. So if we find a new boundary at the upper bound, which is pi, then we see that the cosine here leads to a negative 1. So that's why we have a positive here, and that's factorable. And then the square root and the square cancel, and we would normally see an absolute value here, but because we're positive everywhere that this is evaluated at because of the plus sign, then we can just drop the absolute value. Now for 0, we get cosine of 0 equals 1, so the negative sign's there, so when we factor it, we get little r minus big R squared, and that leads to an absolute value, because that's not always positive everywhere. And again, we can't have the difference be negative because that makes no physical sense when we're dealing with separation distances. So with that, we plug in the substitution, and we get a plethora of cancellations, which is awesome. The square root from the exponential goes away. We have our new bounds here, upper, lower, and then we see that this blue r cancels with that blue r, that sign cancels with that sign, and then we're left with, a pretty stacked integral here, I'd say, but nothing too crazy. So we get y e to the negative 2y 2 over a times y dy dr. And so integration by parts or something like Mathematica, Symbolab, whatever you want to use to get this done, feel free. We see that that leads to a common factor of negative a over 2, and then we can simplify the antiderivative to y plus a over 2 with the exponential term here evaluated at our limits. So a cancels, 2 and 2 cancel, and now we can evaluate this antiderivative at the limits, and finally find the r integral. So we simplify the constants out front, no big deal, we can handle that. Then we have the upper term minus the lower term, and here's where we have to be very careful because of this darn absolute value. So clearly, with the linearity of integrals, we can split this up. And so we have two integrals, one for the upper limit, one for the lower limit. And with that, we see that we can start to separate out the exponential in terms of what we're integrating with. So the big R turns into a common, or just turns into a constant, so we don't need to worry about that. Here, though, since we're running from 0 to infinity, and we see that the minus sign is here, so we keep that width, the absolute value is going to change over its sign at some point. And that clearly is going to change over when little r equals big R. So we have to split this 0 to infinity up from 0 to big R and big R to infinity. And like I said, this is tedious, it's monotonous, it's not necessarily easy to see. And if you want all the little nitty gritty, please check out the PDF because there's a lot of little things that I left out in the video, but you can see the grand scheme of things in the video. That being said, when we look at it from the perspective of 0 to r, we see that it's the negative side of the absolute value, right? We're sloping down, then at r, then we slope back up past r. So we have to put a negative sign on the outside, negative sign on the outside. In this one, we can drop the absolute value because if little r is bigger than big R from big R to infinity, then we don't need to worry about the sign changeover. But that being said, both terms have a negative here. And if we split up the exponentials to just deal with the little r, we see we get the e to the minus 2a big R outside, e to the minus 2a big R outside, and then because we don't have to change the sign on this one inside the integral, or rather from the absolute value, we have a negative negative, which turns that big R to a positive. And so let's be aware, we have a negative on the little r here, negative on the big R, then we have a negative positive, and then we have a positive negative. So it's a whole lot of consideration that needs to be dealt with. Clearly, if we don't split this up into parts like we have labeled here for 1, 2, and 3, it will be very tedious, and calculators symbolically are not going to deal with evaluating these things very directly. So let's go ahead and split this up. We see that we can split the part 1 integral up into two parts, one that has all little r and the other that has the constants. So this is all little r, so little r, blue r, and then exponential blue r, then big R and a over 2 with the exponential. Splitting them up like this, we see that we get another integration by parts or table, however you want to address it. And we kind of saw this form early with that with the theta integral, so we can use it again. Remember we had y e to the negative 2y and all that stuff. So we can do the same thing here, and then we'll evaluate it from 0 to infinity, noting again that exponential at infinity with the negative sign will tend to 0, so whatever this is doesn't matter, which still, mathematically speaking, is kind of handshaky because you get infinity times 0. So, as far as convergence is concerned, this is not, mathematically rigorous, but it's still nice to use it in the physical sense. Then over here, we just get a u sub on the exponential, so that's the negative a over 2. Easy enough, evaluate from 0 to infinity. And after all that, it simplifies to a squared over 2 plus a times big R over 2. Again, all the little details on the evaluation is done in the PDF, but for now, you get to see what we have to do. So with that, we still have part 2 and part 3 to evaluate, so let's see what we get. All right, so breaking this up again into little r's and everything that's constant out front, we see we get the antiderivatives here and here. And, clearly with all, big R being evaluated and 0, we can simplify this pretty nicely. We see here that this exponential has a capital R in it. That's what we see here. Then this one will also have a capital R in it, but after distribution and simplification, we get a quasi-simple thing. We'll just have to pay attention to this exponential later. Okay, so we get another a squared over 2, ar over 2 term, and then another a squared over 2. We'll just have to be careful when combining like fractions and common multiples. Moving on to 3 then, again, little r, everything that's constant. See how we have the big R with the minus sign now due to the flipping of the absolute value that we didn't see here. Antiderivative, integration by parts, another u sub. We have the same kind of process here. Thankfully, with the infinity, a lot of these exponentials go to 0, so we don't have to worry about the r terms. And that simplifies to a squared over 2 with an e to the negative 2a times r. Now we can plug all of this in back into the direct integrals. So we had the e to the negative big R, e to the negative big R, and then e to the big R with a positive, negative, negative, just to make sure we're all on the same page. And as we see here, we have a common factor in this term. Let me get color. That exponential and that exponential, so we can simplify everything that's in the fractions together. That's what we see here. We factor that exponential out, and now we can see common factors. We see that we have an a squared over 2 here, and a squared over 2 here. That's nice. AR over 2, AR over 2. Cool. Like I said, we're going to have to deal with this exponential in the next step. But we see that we have a positive argument here, a negative, or the negative argument here with the positive argument. Let me go to laser. We have negative, positive, and as we see here, this positive, this negative, that'll cancel that exponential to e to the 0, which is 1. So we'll have to do that on this exponential as well. And then we could actually simplify everything in the curly brackets. All right, so as promised, we combine the fraction terms, hence the a squared over 2. You have 2 copies of those, easy enough. 2 copies of these. And now we need to go ahead and simplify down. We can yeah, we'll go ahead and simplify down, and we see that after we distribute this exponential into that one, then we get a negative a squared over 2, and this negative a squared over 2, hence the negative a squared, since we have 2 copies of those, since the exponentials cancel. Okay, like I said, that was my forewarning in the last slide. After that, we just have to distribute this negative 1 over AR, and we see that factor of A cancels with factor of A. This, the whole fraction here cancels with that, but we have a negative there to account for, so we end up with a negative 1. And then we have a negative negative here canceling from the red negative, and then a factor of A and A canceling. So after all those cancellations, we get an A over R here from this term, because negative negative puts that as a positive. Then the exponential term, we have to factor out a negative, so that negative and that negative go right there. And then we have a over r from this, and just a 1 from that. And if we put this in form matching term for the book answer, we get equation 8.48, which is exactly right. So thus, we found the direct integral for the setup, and that allows us to move on to the exchange integral. Now, as you'd imagine, you're going to have pretty much the same setup and solution style, so we can just kind of streamline through it now. With the exchange integral, with having R1, R1, and R2, remember that we're now putting, with geometry, R is proton 1 to the electron, and R2 is the R prime that we had from law of cosines. So when we plug everything in, after we plug in the wave function, we're good there. We see the normalization. This is from proton 2 to electron. So we get the exchange between those two. Pretty cool. Excuse me. And then we see cancellations, of course. We're running the same scheme here. So split it up, get your Jacobian, cancel, cancel. phi integral, let that run through now, simplify as much as you can. The only difference now that we didn't have last time is that we have an e to the negative r out front, because we have this thing in here because the exponentials did not combine this time. We have r1 and r2 here, so we can only apply the exponential with the law of cosines, and then we're going to have this one left over. So instead of a little r only on the outside, we have an exponential term with it. Don't worry though, we're going to end up with the same thing that we saw last time, except we're going to have a different factor of e on the outside. So let's see what that looks like. Oops, yep, that's equation 8.47. All right, so using the same substitution for y and d theta, we see that we get our y of pi for the new limits and y of 0. We get the same thing, so we're good to go. All right, with that then, applying the substitution, same thing, little r cancels, sine and sine cancel, and now we're left with, see how we end up with the same y integral now? So that's going to be integration by parts. The only difference is that we don't have a negative 2 over a, we just have a negative a. So that's the factor there, cancel, cancel. That's our factor there, no big deal. And then we have to evaluate at the bounds. So to streamline that, we do that, and then we split it up because of this absolute value that we're going to have to deal with. And now you see that we can combine the exponential from beforehand and the evaluated exponential. Same thing here. We have the absolute values up here. So once we split this 0 to negative or 0 to infinity up, we're just going to pull out all the exponentials and streamline it. Again, in the PDF, this is more step by step, so you don't have to worry about it. But you still see the same landscape that we did on the direct integral. So now we can just utilize that and save ourselves time. All right, so splitting that up, we see we get all of that, 0 to r to infinity, just like before. We had to switch these terms in terms of their signage. Instead of a negative sign, we leave that alone, so we're good. Now we can take out, instead of having 2a with big R, we have a just big R over a, positive, negative, negative. And then in here, we get back to negative 2a because of the evaluated exponential and the expectation exponential. All right, and then we have a nice cute 0 here, so that goes away. We like that. We can deal with that much easier. That being said, we do the same trick here. Split up the integral 1 for everything that deals with little r, all the constants, and we get the same result. So once you set the landscape initially, you can use old results and save yourself a ton of time. This will be very tedious if you're writing it out by hand, but once you write it out, or type it out rather, then you could just copy and paste and it saves you a ton of time. And it looks neat because I'm sure most of us don't have pleasant handwriting. That being said here, another u sub on it, easy enough. But that evaluates the 3a squared over 4 plus a times big R over 2. That'll be easy. Clearly, we don't have to do much here because we don't have any exponentials here because of the negative r, positive r. That cancels to e to the 0. Wonderful. So just tag everything with a little r and then evaluate from 0 to r. Simplifies to r squared over 2 plus a times big R. That was surprisingly easy. Again, all the work is in the PDF, so please feel free to use it. Now on to the last one, where we have the r and then the a minus big R from r to infinity. Again, integration by parts here. U sub here evaluates the 3a squared over 4 e to the negative 2a times big R. So again, we're going to have to deal with that with distribution, and we'll be good to go. So putting this all together then, what we see is that the exchange integral measures negative 2 over AR, the simplified result from integral 1, simplified integral 2, simplified integral 3. We see that we get, again, the common factor of these exponentials here and here, factor it out so that you can simplify the parentheses. All right, so we have a 3a squared over 4, and then we have an AR here, and R squared in the middle. This and this will combine. This or rather, this will be left alone, this will be left alone. The AR and AR term here will be combined, hence the finding common denominator. The other side, we just take this e to the positive r over a and add it with the negative 2a times r, so that'll simplify nice. After that, what we observe here is that, well, what this boils down to is a negative r over a, so then we can actually factor this one out, and it leaves us with the negative 3a squared over 4, which we see here, and that cancels with this one here. This is simplifying very nicely, and it's almost concerning. Okay, but after we simplify this one down, you see we get the negative here, hence the red negative. Then we have the negative r squared over 2, but clearly, since we have this multiplication of the constants out front, we have a negative and a negative canceling, 2 over 2, big R over big R. So after that, we can distribute the 1 over a into everything. And when we do that after the fact, we see that we get a and a cancel, and then we have an r over a term. And this gives us equation 8.49, which is exactly the book answer for the exchange integral. How cool is that? Again, the direct integral showed us exactly what we needed to do, and the exchange integral, we just ran through the same template, thankfully, and we actually get some simplified results. Do not rely on the computers to evaluate these things in the the absolute most general form. You're gonna have to split these up because symbolically that's too much for them to deal with. But once you do that, it's pretty easy after. All right. Well, in summary, we saw how these things are at least evaluated. Again, the notation and such makes it to where it looks intimidating by its naivety and simplicity initially. Then once you plug everything in, especially with the geometry of the law of cosines in this case, it looks absolutely daunting. But the actual application of the integrals is just an integration by parts and a u sub. So those two things are not that bad in and of themselves, but in a bigger landscape, it made this a very tedious problem. So as always, try to break them down into smaller and smaller increments to help you, because if you don't, it will be a cluster, and you don't want to deal with clusters. You want to be able to have a nice streamlined process and not have to second guess anything. And sometimes breaking them down into sub problems makes it a whole lot more simpler. So don't feel needed that you need to evaluate these things in all one form. Take your time, split it up, understand what's meant with the absolute value and where it comes from, especially with square roots and squares. That being said, you know, these problems do take a while, so I need to give a massive thank you to all my supporters for making this possible. I'm extremely grateful for your support. If you'd like to see more, you can also become a patron for access to supplemental material, current and future projects, and one-on-one help, especially with the new school year rolling in the fall in a couple weeks. That'll be very much needed. New content is posted weekly to fuel your curiosity, especially because I'm going to start using more of the math and incorporating that with the coding aspect of these problems. So I'll have to do a part 2 of these problems with the computer problems. That'll be really fun so you can see how to use computational methods, especially numerical analysis. And quite frankly, if you're not at least decent at knowing how to problem solve with computers and coding, some of the higher level stuff, as you see, is just not very applicable without computers. And I'm thinking like second and third level corrections and perturbation theory. That's just, you're going to need a computer. Same thing with the 18 by 18 matrix we saw in the Zeeman effect. You're going to want to have a computer help you diagnose those things, because what happens when we have an n equal 4, right? So then you have 2 times n squared. That's what? 16 times 2. So 32 states to consider instead of 18. That is a 32 by 32 matrix. No one wants to deal with that by hand. So utilizing the tools that we have now will make our lives easier later, although it's very frustrating on the learning curve, but it's much better to have that curve done early than later. So we'll have to tinker with that here soon. That being said, Books, notes, and other reference materials will be found below in the description because none of these things happen by themselves. There's a lot of collaboration, and it's often easier to help people, in my experience, by giving them more resource than not enough. Um, but you have to give it in such a way that it answers the little marginal questions, not the big picture questions. Otherwise, it's too much and it's overbearing. So if you have any questions about that, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.